Hello everyone, and welcome to the video I've made for some really additional vectors. This is not material you're going to find necessarily in the book. The ideas are the same as what we've been working on, but we're going to deal with some three-dimensional vectors plus look at some vector equations of the lines. So the skill objectives for this particular video are: 1, we want to perform vector operations on vectors in 3-space. 2, find vector equations for lines on a plane or in space. Number 3, use vector equations to find parametric equations of a line. And number 4, determine if lines in space are parallel, intersecting, or skew. The conceptual objective for this one is really to understand that the vector calculations that we did in the two-dimensional vectors are going to be almost the same, slight modification to do the 3-space calculations. Before we go on, I do want to refresh your memory on a couple things. These are things you've been working on. Number 1, when we're dealing with two-dimensional vectors, I'm going to let u be the vector u1, u2, and v is the vector v1, v2. So if I do vector u plus vector v, it's just really adding the corresponding components together. And if I take a scalar times a vector u, I just distribute that scalar to each component of u. And the dot product of u and v is going to be the product of the first components plus the product of the second components. Now remember, those first components are the horizontal component, and the second one is the vertical component. And the last thing is that the magnitude of vector u is the square root of the horizontal component squared plus the vertical component squared. Also, I can find a vector, the component form of a vector, when I know 2 points, the starting point and the ending point. So in this case, starting point at A, ending point at B. I know the vector that goes from A to B is going to be x2 minus x1, and then y2 minus y1. In other words, the horizontal component is just going to be the difference between the two x coordinates, and the vertical component is going to be the difference between the two y coordinates. So now let's look at what happens when we deal with three-dimensional vectors. So in this case, I'm going to let u be the vector u1, u2, u3, and v be the vector v1, v2, v3. Well, I can add those two vectors, and very similar to what you just did, when we added vectors in 2 spaces, we added the corresponding components, and that's the exact same thing we're going to do here. If I take vector u plus vector v, it's going to be u1 plus v1, u2 plus v2, and then u3 plus v3. If I do a scalar multiple times vector u, I'm going to multiply each component of u by that scalar, and if I'm going to do the dot product, it's going to be where I take the product of the corresponding components and add them together. So u1 times v1 plus u2 times v2 plus u3 times v3. The magnitude of vector u, very similar to what you dealt with in 2 dimensions. In 2 dimensions, we did the square root of the sum of the squares of each component, and that's the same thing that's going to be true when we deal with the magnitude of vector u. It's going to be the square root of u1 squared plus u2 squared plus u3 squared. Another thing is that when we have 2 points in 3 dimensions and I want to find the vector between them, I can do that the exact same way we did before. I have a point A that goes from x1, y1, z1, and a point B that goes from is at x2, y2, z2. And so the vector that goes from A to B is going to be x2 minus x1, y2 minus y1, and z2 minus z1. Let's take a look at a couple examples. In this case, what I have is I have a point A in 3 dimensions, which is at 1, 3, negative 2, and a point B at 4, negative 1, 7. Now the first thing I want to do is find the vector that goes from A to B. Well, it's going to be, so in this case, it's going to be 4 minus 1. Take the first component, subtract them, the difference between the second components, and then the difference between the third. So 4 minus 1, negative 1 minus 3, and 7 minus negative 2. And that vector then comes out to be 3. The vector is 3, negative 4, 9. Now, the magnitude of AB is going to be the square root of 3 squared plus negative 4 squared plus 9 squared, which equals the square root of 9 plus 16 plus 81, which will give us the square root of 106. Now, in terms of, let's look at two vectors u and v. U is equal to the vector 2, 1, 4, and v is the vector -3, 2, -1. So u plus v comes out to be 2 plus -3 plus 1, or then 1 plus 2, and 4 plus -1, and which gives me -1, 3, 3. And u dot v is going to be 2 times -3 plus 1 times 2 plus 4 times -1, which comes out to be -8. Now, all the things that you dealt with in the last section in terms of the angles between two vectors, and when the vectors are orthogonal or not, are still going to be true. I know, even in 3 dimensions, that the angle, that the cosine of the angle between the two vectors is going to be equal to the dot product of u and v over the magnitude of u times the magnitude of v. I also know that if the dot product of u and v equals 0, then the vectors are orthogonal. And v are orthogonal, which again meant that they were perpendicular. One other change that we do also have with this between 2 dimensions and 3 dimensions is the whole special unit vectors. We can still find a unit vector in 3 space by dividing each component by its magnitude, just exactly as we did in 2 space. But we do have these special unit vectors. In 2 space, our special unit vectors were I, which is a vector 1, 0, and j, which was a vector 0, 1. Now in 3 space, because we have 3 components, there is going to be a third unit vector. I now is in 3 space, it's going to be the vector 1, 0, 0. J is the vector 0, 1, 0. And k is the vector 0, 0, 1. And so what you're going to see is they will define vectors in terms of I, j, and k. In this case, I have the vector u, which is 3i minus 5j plus 2k. And so I can, if you want, you can translate that into the other notation that we have, that we've been using, and you can think of that as 3, -5, 2. J would be the vector, is the vector -2i minus 4j plus minus 7k. And so, in this case, vector v is equal to the vector -2, -4, -7. You should be familiar with both notations and being able to translate between the two, because you will be asked to do that on the worksheet that I'm going to give you in class. Now let's deal with vector equations of a line. Now when we're going to first look at lines on a plane, the way we usually look at lines, and we're going to have we're going to let A be a point on the line, and A is the point x1, y1, and the slope of this line is going to be p over q. Now it's important to remember that when we deal with vectors, the first component is the horizontal component, the second component is the vertical component. And so when you look at slope, slope is rise over the run. Well, the run is the horizontal component, and the rise is the vertical component. And so when we do this, the vector equation of the line is going to be the vector xy equals my point vector that I know, x1, y1. So just taking that point, writing it as a vector, plus t times the vector, our slope vector, which is our horizontal component q and our vertical component p. Now, the other way of writing vectors, and you'll see this a little bit more in this with these problems here, is going to be, instead of this notation, it will be written in this form here. And one of the things this then does is some calculations allows us to get what are called parametric equations. In parametric equations, you actually have the x and y coordinates of a point are actually going to be written in terms of a third variable or parameter. In this case, it would be t. Let's take a look at how this works, and then we'll come up with the parametric equations here too. So I don't want to do it with the last ones because there'd just be so many letters. So let's look at this where we have the numbers. In this case, we're going to find a vector equation of a line that goes through the point A, which is 2, 1, and B, which is negative 3, 4. The first thing I have to do is find that slope vector. Remember, the slope vector is the horizontal component and then the vertical component. So the horizontal component first, the run. And really what you have to realize on this is that that slope vector, which is m, like that, or is going to be the same thing as the vector that goes from A to B. So in this case, when I do that vector from A to B, I get the vector negative 5, 3. And so my line is going to be xy equals my slope, a point vector. Technically, you can use either A or B. I'm going to choose to use A. 2, 1 plus negative 5, 3 times t. Remember in this case that this is my point vector and that is my slope vector. Now, what I can do at this point is I can go through and apply vector operations, in this case scalar multiplication with the t and then the vector addition, to come up with two equations, for an equation for the x-coordinate and then the equation for the y-coordinate. So what I'll do, first we'll deal with the t. That would tell me, I know that xy is equal to the point vector 2, 1 plus negative 5t, 3t. Just using the idea of scalar multiplication. And so I now would have that xy equals, when I add the two vectors, I add the corresponding components, I'm going to get 2 minus 5t and 1 plus 3t. So in this case, I now can say I have the parametric equations for this line. I know that's going to be where x equals 2 minus 5t and y equals 1 plus 3t. Now what these parametric equations do for us is it allows us to go and come up and put a direction on a line as well as put a timestamp in terms of this. Because I can say, I can let t, my parameter, represent time. So when time is 0, that's where I'm going to start. So in this case, when time was 0, I started at A. And then when I put in 1 for t, I will get the place where we would be after, like, let's say 1 minute or 1 second. When I put 2 in for t, I get another location. And so I do get direction as well. Let's take a look at how this same procedure is modified with a three-dimensional when we deal with a line in space. In this case, we have a line in space that's going to go through the point A, negative 2, 4, 7, and B, 5, negative 1, 3. And again, our slope vector is just going to be the vector that goes from A to B. And that's also why I end up, for my point vector, I always end up choosing A, because that's where I'm going from A to B. So the vector I'm going from, I'll let that be my initial point. And so it's going to be, when I find that vector from A to B, I get 5 minus negative 2, then negative 1 minus 4, 3 minus 7, and I get the vector 7, negative 5, negative 4. And so in this case, x, y, z, because it's in 3 space, equals negative 2, 4, 7 plus 7, negative 5, negative 4, t. Or I can go through on this one, same thing I did before. I know that x, y, z equals negative 2, 4, 7 plus 7t, negative 5t, negative 4t. And then really solving that, I can get that x equals negative 2 plus 7t. I know y equals 4 minus 5t. And z is going to be 7 minus 4t. And those would be the parametric equations in space for this particular line. Now, in terms of lines in space, you really have 3 different things that can happen. Number one, they could be parallel lines. Parallel lines are going to be lines that obviously never intersect, but they're going to be ones where their slopes are going to be scalar multiples of each other. So if I look at their slope vectors of them, they will be scalar multiples of each other. Number 2 is going to just be intersecting lines. Lines intersect in space. And that's, you can take 2 pencils. Take one pencil in your left hand right now, one pencil in your right hand right now, and put them so that they're touching. And you will have 2 lines that intersect in space. The third one is skew lines. Skew lines are lines that are not parallel, but they also do not intersect. For example, if I look at this particular cube here, you'll see I have one line here which forms this corner of the cube, and another line that forms that corner of the cube. Those lines are skew. They are not parallel. They don't have the same direction, but they also never intersect. Okay, so it's basically you can do this too if you have take a pencil in each hand, hold one so that it is vertical, hold another so it's not vertical, and keep them separate, and that you would then see skew lines. You would have the pencils would represent skew lines. Now what's going to happen is that we're going to give you the parametric equations for two lines in either, well, in this case, in three space it will actually be. And you're going to have to determine if they are parallel, if they are intersecting, or if they are skew. Well, the first thing you want to do is determine if they're parallel. And in this case, we have 2 lines that are not parallel, but I want to show you how you go through and determine if they are. What you're really going to do is look at the slope vectors. Remember, the slope vectors are formed by the coefficients on the parameter. So in line 1, our parameter is t. And so our slope vector is going to, the coefficients there are 2, in this case -1, and here 1. So my slope vector here for line 1 is the vector 2, -1, 1. Now when I look at my second line, the coefficients on the parameter, which in that case is s, are 3, -1, 2. So my second slope vector here is the vector 3, -1, 2. Now in this case, there is nothing that I can multiply every component of my first slope vector by to get the components in my second slope vector. Like if I could multiply 2 by 3 over 2, or 1.5, that would give me 3. But if I take 1.5 times -1, I'm not getting -1. If I take 1.5 times 1, I'm not getting 2. So I don't have, we know that these 2 vectors are not scalar multiples of each other. And so therefore, I know that I know that these lines are not parallel. Another thing I could do is take these slope vectors, I could just find the angle between them. If they're parallel, the angle between them is going to be 0 or 180 degrees. Whereas if it doesn't come out to be that, then I know that they are not parallel. Now what we're going to do at that point, once we've determined that they're not parallel, we can then go through and we're going to assume they can intersect. And when I do that, what that means is that if they intersect, that there is at some point that the x, y, and z components are going to correspond. So that there's some value for s and t such that this 1 plus 2t would equal -2 plus 3s. So I set those equal to each other. I do the same thing for the y components. 2 minus t equals 3 minus s. And z, 3 plus t equals 1 plus 2s. And what I did at this point is I just went through and algebraically got the variables on one side, the constants on the other. So I did some algebraic manipulation, and this became 3s minus 2t equals 3. This one here became s minus t equals 1. And right here, this becomes 2s minus t equals 2. And now what you're going to do is you're going to pick 2 of these. You got 1, 2, or 3. You're going to pick 2 of those. And you're going to solve, that's going to be a system of equations that you solve back in Algebra 2. And I think you probably did some in Algebra 1 as well. And you're going to solve that system. You can use substitution, you can use elimination, whatever you choose. You're going to solve that system, and you will get a solution to that system. Once you have that solution, you're going to check that in the third equation. If the third equation comes out to be true, then you know that the lines intersect. If when you check the solution in the third equation you get something that is not true, you know the lines are skew. Now you do have the choice on which ones you want to solve. In this case, I'm going to choose to work with the second and third. I'm going to end up doing elimination. So what I'm going to have there, I am going to have s minus t equals 1 and 2s minus t equals 2. And what I can do on this one is I can go and like I said, I'm going to do elimination. I'm just going to multiply one of these equations by -1 so that the t's will end up dropping off. So I'm going to make that, I'll multiply the top equation by -1. So that's going to end up changing all the signs. So I'll make that negative, positive, and then a negative. And then I'm just going to add this up. So negative s plus 2s is going to be 1s. So I'll just get s. T minus t is 0 equals -1 plus 2 is 1. So right now I know s equals 1. If s equals 1, and it doesn't matter which one I go to, I can go back to this equation right here, and I'm going to put 1 in for s, which will give me 1 minus t equals 1. And then solving that for t, I'll subtract 1 from both sides. I get negative t equals 0, so t equals 0. So now my solution that I have right now is that s is equal to 1 and t is equal to 0. And what I now need to do is check that solution. So I'm going to go through. Remember, I used this equation and that equation to find the solution. So what I'm going to have to do now is I'm going to have to go to this equation here. And I'm going to put 1 in for s and 0 in for t and see if I get a true statement. So in this case, what I have is that 3s minus 2t equals 3. Putting 1 in for s, 0 in for t, I get 3 times 1 minus 2 times 0 equals 3. And sure enough, I get 3 minus 0 equals 3, so 3 equals 3. So in this case, because that statement here is a true statement, I know that these two lines actually do intersect. There are two lines in space that will intersect. This now does conclude the video I have for working with these vectors in 3 dimensions and these types of equations. We'll probably do a couple of other examples because there's some story problems and stuff that we'll look at. But for the most part, the calculations that you have to do are going to be very similar to what you have here, what we've seen here. So with that, I hope you are all having a good time, a good day, and I will see you at our next class.